Okay, in this video, we are looking at a method for converting a DFA and an NFA. If you're given with a DFA or an NFA, you can convert it into a regular expression using a method called Arden's theorem. Okay, so we'll look at Arden's theorem, its proof, and some solved examples where we convert a given DFA and an NFA to a regular expression. Remember, Arden's theorem is one of the ways for converting a given DFA or an NFA to a regular expression. So there is one more method called the state elimination method, which we'll look at in one of the future videos. Now, before actually getting into the Arden's theorem, let's understand the ways of converting a given FA to a regular expression. So given an FA, we can convert it into a regular expression using two methods. One of the methods is by using the Arden's theorem. Okay, remember that very importantly, the Arden's theorem cannot be applied in epsilon NFAs. So you can apply Arden's theorem only for DFAs and NFAs. And DFAs and NFAs it can be applied, whereas in epsilon NFAs, if you are given with an epsilon NFA, you cannot apply Arden's theorem to convert it into a regular expression. So there is one more method called the state elimination method. So in this method, we can actually convert any given FA to its equivalent regular expression. So it can be a DFA or an NFA or an epsilon NFA. So there is no restriction on the type of FA that you want to use here. So the state elimination method can be applied to any given FA. Now let us look at the Arden's theorem. So according to Arden's theorem, if P and Q be two regular expressions over sigma, the alphabet set, and if P does not contain a null string, that is epsilon, then R equal to Q plus RP has a unique solution, that is R is equal to QP star. So if you are able to write R equal to Q plus RP, so if you are able to represent R in the form Q plus RP, then according to Arden's theorem, it has got a unique solution, that is R equal to QP star. So the unique solution is R equal to QP star. Okay, so remember R, everything P, Q, and R, all these are representing regular expressions. And very importantly, P should not contain, even though P is a regular expression, P should not contain epsilon. That's an important condition here. P should not be epsilon. Now let us look at a proof for Arden's theorem. So even though it's not a very pure mathematical proof, let's go through this. So according to Arden's theorem, if a regular expression R can be written as R equal to Q plus RP in this form, then R equal to QP star is a unique solution. So remember, P cannot be epsilon here. So based on this, we will prove this. So let's put back this solution. So what we'll do first is that we will put this QP star, R equal to QP star, back in our original relation, that is R equal to Q plus RP, and then verify that this is a valid solution. So we can do that. So what I'm going to do now is that I'm going to replace R with QP star in equation 1 in 1. So if I do that, I will get R as R equal to Q plus, so instead of R I am putting back QP star. So QP star into P, this is what I get. Now if you concatenate this one, you'll get Q plus QP star into P. And now you can write this as, you can take Q outside and once you take q outside, it becomes epsilon plus p star into p. Okay, now we can actually identify that epsilon plus p star into p. So this means, so we know that p star into p is nothing but the positive closure of p. This is nothing but p plus. Okay, so when you have a union of epsilon and p star, p plus, that's a positive closure of p. Okay, so when you have something like epsilon plus the positive closure of p, then that is equivalent to p star itself. So that becomes, so this can be written as q into p star. Okay, so we could actually prove that if we put back q p star as r in our original expression, it becomes valid. So our step 1 is complete now. So we can verify that the solution r equal to qp star is a valid solution. Now we also want to prove that this is a unique solution. So we'll do that in our next slide. Now, to prove that QP star is a unique solution, what we are going to do here is that we are going to put back the value of R as just Q plus RP again in the same equation. So if you consider this as equation 1, and we are going to put back putting R equal to Q plus RP in 1. So here we have an R here. So if you look at the equation, so instead of this R, we are going to replace it with Q plus RP. So what essentially we are going to get here is R equal to Q plus RP into P. So if you concatenate this, it becomes Q plus QP plus RP squared. Now again apply the same thing. Again replace R in, so consider this as 2. Consider this as 2. And again putting R equal to Q plus RP in 2. So if you put it in 2, then it becomes R equal to Q plus QP plus Q plus RP in concatenated with P squared. Okay, that is going to be Q plus QP plus, now if you concatenate, becomes QP squared plus RP cube. Now if you generalize this is going to be, again if you put back R equal to Q plus RP, so this is going to be a series. So the series will look like something like this. It's going to be QP plus QP squared plus etc. plus QP raised to n plus R into P raised to n plus 1. Okay, so this is what we are going to get here. Now look at this. So you have powers of P, and finally you have R into P raised to n plus 1. This term that is left with you. Okay, so now we can easily see that if you replace R with QP star, so if you to satisfy this, the only replacement possible for R is going to be R equal to QP star. So if you put R equal to QP star back in this equation, so it becomes Q plus QP plus QP squared plus QP raised to n plus, now instead of this R, if I'm putting it as QP star, so it becomes QP star into P raised to n plus 1. Okay. Now we can take Q common here. Q can be taken as common. And now we can write this as Q into epsilon plus Q into epsilon plus P squared plus etc. plus P raised to n plus P star into P raised to n plus 1. Okay, so we know that this particular term, the entire term here, that is epsilon plus P squared plus this particular term here is going to be this particular term here is going to be nothing but P star. This is the closure of P. This is closure of P itself, and the closure of P is P star. So you can replace this by writing. You can replace this as by saying Q into P star, because the closure of P is nothing but P star. So this is going to be Q into P star. So this is how we can prove that QP star is a unique solution. So what initially we did is that we proved that QP star is a valid solution, and then we also proved that this is going to be a unique solution. Okay. Now let's look at how can we apply Arden's theorem for converting a given DFA or an NFA to a regular expression. So here we are given with a DFA. Okay. So the first thing that we need to do here is that we need to write the expressions for each of the states. In this DFA, we have got two states, A and B. So we'll write the expression for A. So we'll start with A. So, looking at A, since A is a starting state, it always contains epsilon. That means, we can write A as equal to epsilon, because just by seeing an empty string, you are already at A. Plus, if you look at this DFA, so we can identify that from B, if you look at here, from B upon getting a 1, we can reach A. So B dot 1 is also a possible way of reaching A. So that also you need to include here. So epsilon plus B dot 1. Similarly, we have to write the expression for the state B. If you look at the state B, there is only a single path from state A to B upon getting a 0. So that's the only way of getting to B. So we can write the expression of B as A dot 0. Now let's call this as equation 1 and this as equation 2. Now we can put you can put the value of A, putting 1 in 2. You can actually put, you can see that this value here represents the value of A, and here also you can see an A. So you can just put this value here in this A. So doing that, you will get it as B equal to epsilon plus B dot 1 into 0. Okay, so now this becomes epsilon 0 plus B dot 1 dot 0. So we know that epsilon 0 is nothing but 0 itself. So 0 plus B dot 1 dot 0. So if you look at this expression that we have derived here, if you look at this expression, then we can identify that this is in the form of the Arden's theorem. That is, if you look at this expression, you can identify that you can consider B as R. So wherever you find B, so here again you find a B, you can consider this as R, and this 1 dot 0 you can consider this as P, and this 0 you can consider this as Q. Okay, so if you look at the expression, if you look at the expression that you got, it's in the form of the Arden's expression. So now we can apply the Arden's theorem. So according to Arden's theorem, the solution for this is going to be R is equal to QP star. So in the expression that we have, Q is nothing but 0. Q is going to be 0 and P is nothing but 1.0. So 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 we can write B as 0 into 1.0 star, and this is going to be our solution for B. So this is how we remember B is our final state. B is our final state, and we want to find a very simplified expression for B. That's why we ended up in finding the expression for the final state B as 0 into 1.0 star. This is how we can make use of the Arden's theorem to, to actually convert a given DF or an NFA to a regular expression. Okay, now let's look at another question. So in this question, the specialty here with this FA is that this is, if you look at this, this is not an DFA, this is an NFA. Because if you look at B, the state B, transition on A goes to B itself, and also it goes to C. Okay, and also you have got two final states here. Your B is a final state. Similarly, C is also a final state. Now, when you make a regular expression for this, you have to combine. You have to create a union of the regular expressions for both B and C, because both B and C are final states here. So you find a simplified regular expression for B union the simplified regular expression for C will be your answer. Because here, the difference is that you have both B and C as final states here. So here in this NFA, you can see that it does not have a single final state, rather it has got two final states. So we have to consider the simplified regular expressions for both the final states, which are B and C here. So let's start working out. Okay, so let's start by writing the regular expression for A. So if you look at the state A, it can be epsilon because it's a starting state, epsilon plus, if you look at the state A, the way to reach state A is just by having a transition on A, it gets back to A itself. So we can write it here as AA. From A, if you get A, you'll be reaching back to A. Okay. Now, if you consider this regular expression, you can identify that it's nothing but A star. Okay, because it can take either the value epsilon or AA. So AA again you can substitute for A here, so that the definition becomes recursive, and you can verify that this is nothing but A star. Okay. Now let's write the expression for the state B. So if you look at closely in the NFA given, you can reach to B via, if you're at state A, if you get a simple B, you can reach to B. Okay, so let me write down that path. So it's going to be A and A with the alphabet B. Now there is one more way to reach B. Okay, so if you look at B itself, the transitions on both A and B are defined back to B. So that means if you're at state B, if you get either an A or a B, you will be coming back to the state B. So the equivalent way to express it is B into A plus B. So it means that you can reach to B, the state B, by either seeing a symbol B from the state A or seeing A or B from the state B. These are the only possibilities of reaching to the state B. Now we can actually write the expression for the state C also. Okay, if you write state C, so if you look at the paths, so if you get an alphabet A, get a symbol A from the state B, you can reach to C. That's one way. So let me write that first. So If you are at state A and if you get a symbol A, then you'll be reaching C. Then one more option is that if you are at C and if you see any of these symbols, A or B, you'll be reaching back to C itself. So to express that, we can write it as C equal to BA plus C into either an A or a B. Both of them are okay. Okay, so we have written equivalent expressions for the state A, B, and C. Now let's try to substitute it. So if you look at B, if you can. So since we know that from here we know that A is nothing but A star. Okay. Now we can put this in our expression, in this expression. Okay, so if you put it there, then what we are going to get is B equal to, instead of A, we can write it as A star. A star. Instead of A, we can write it as A star and A star into B. So what I did is I replaced this A with A star. Okay, so you can see it here. And now you can write it as plus, okay, plus B into A plus B. Okay. Now, if you closely watch this expression, you can understand that this is in the Arden's format. So you can consider this as a this as P, this as Q, and this as R, and you can verify that this again is repeating here. That's R. Okay. So in the place of R, you have B. In the place of Q, you have A star B. In the place of P, you have A plus B. Okay. So if you apply Arden's rule to this expression, then we can easily derive this as, we can say that this B is going to be QP star. Q is nothing but A star B, and P is A plus B. So A plus B star. So this is nothing but QP star. Okay, so A star B was our Q and A plus B was our P, and so it is P star is going to be A plus B star. Okay, now that we got B, okay, we can put this back in the expression of C. Okay, so what I'm going to do here is, so suppose this is okay, what I'm going to do here is that I am going to substitute this B in my expression for C. So the expression for C will become C equal to A star B into A plus B star. Okay, so this whole thing represents B into A. So when I say into, it's actually concatenation, plus C into A plus B. Now, if you watch this expression again, this is also in the form of the Arden's format. So this, if you consider C as R, C is repeating here, and you can consider this A plus B as P, and this whole expression you can consider it as Q. So R equal to Q plus RP. So this is in the same format. Now we can equivalently write C as QP star. So we know what is Q, we know what is P. So QP star is going to be, so if you can simplifying this using the Arden's theorem, becomes A star B into A plus B star into A. This is our Q, and this is our P. So A plus B star. Okay, so this is going to be the expression for C. And remember, very importantly, we have both B and C are files. Okay, so when you write the regular expression for this particular NFA, it has to be a union of the regular expression for B and C. So we know that this is the regular expression for B. This is the regular expression for B, and this is the regular expression for C. So we have to actually combine them using the union. Okay, so union is nothing but the plus operator. So the final solution, the total solution of this question, that is the equivalent representation for this particular NFA is going to be actually the regular expression for B plus the regular expression for C. So that would be the final solution would be like this. So it is going to be A star B into A plus B star, So this is, and plus this one, that is A star B into A plus B star into A plus B star. Okay, note that this particular term corresponds to the expression for B, and this term corresponds to the expression for C. Okay, so that's why we are combining them, and this is going to be our total solution. So this is our total solution. So remember to, when you have two final states, remember to apply this union operation. So since in this case we had both B and C as final states, we have simplified the state B using the Arden's theorem. We have also simplified the state C using the Arden's theorem. And after simplifying, you have to combine them using the plus symbol, because the total solution is going to be a union of both of them. Okay, so that's why it's very important to note that you have to combine the final states using the union operation or the plus symbol when you have two final states, two or more final states. Okay. Now let's look at another question. So in this question, we are asked to construct a regular expression for binary strings that does not contain, so very importantly, it does not contain 1 as a substring. So if the question was about to design the binary strings that contain 1 as a substring, it would have been very easy. But here the question is which does not contain 1 as a substring. So we cannot actually solve it trivially using the basic approaches that we do while looking at a question. Okay, so what we can actually do here is that we can design a DFA for accepting strings that contain 1 as a substring, and then take a complement of that DFA. So we have already learned how to take a complement, how to create a DFA for complement representations. So we can actually start building the DFA. So the procedure for approaching this question is going to be like this. So create a DFA for the normal form, and then let me write it down so that it becomes clear. So the steps will be like create a DFA for the normal form. Remember, it is not very easy. It's not very trivial to directly create the DFA for this. So what we are doing here is create a DFA for the normal form. That means normal form means strings that contains 1 as a substring. Okay, so this is the first step. So let's create it and go. Okay, so if you create a DFA for the normal form, it will be something like this. So start at Q0, starting state is Q0, and from here, trivially, if you get a 1, you go to Q1, you get another 1. Let me make it clear. So if you get a 1, go to Q1, and if you get one more 1, you can go to Q2, and that's going to be your final state. We have to also represent all the transitions from Q0. If you get a 0, you can stay back at Q0. So this is nothing but the DFA design. So from Q1, again, if you're getting a 0, you have to go back to Q0. And from Q1, from Q2, if you're getting a 0 or a 1, you can stay back at Q2 itself. Okay, so this is how we design a DFA for accepting binary strings that contains 1 as a substring. Now it becomes very easy for us to convert it to a DFA that does not contain 1 as a substring. Okay, so so that will be something like this. So the only thing that we need to do here is to obtain the complement form is that we have to convert all the non-final states into final states and all the final states into non-final states. So here we have Q0 and Q1 as non-final states. So we have to make them as final states. So the equivalent DFA will be Q0 is going to be a final state here. Q1 is going to be a final state. So this is something which we have already looked at in the early part of our course. So Q2 is a final state in our normal form. So Q2 is going to be a non-final state. All the transitions will remain the same. Okay, so we can go back to 0 here. All the transition, there's nothing, there's no change in the transitions. So here is going to be a 1, and upon 0, 1, you are going to stay at Q2, and from here you have a transition of 0. Okay. So this is going to be our DFA for the complement form. So this will represent the DFA for accepting strings that does not contain 1111 as a substring. Okay, so now it becomes easy for us to generate a regular expression from this DFA. Okay, so now you are given with a DFA which actually represents the language given in the question, and then we can actually try to convert this into a regular expression using the Arden's rules, Arden's theorem. Okay, let's write the expressions for Q0. So let's start to write. So by looking at this particular DFA, we can actually start writing the expressions for each of the states. So we are interested in two states, Q0 and Q1. So we have to combine the solutions for both Q0 and Q1 so that to obtain the complete solution. Okay, so let me start writing Q0. So Q0 is going to be, if you look at the diagram here, DFA diagram here, you can understand that Q0 is a starting state. So epsilon is a valid transition. So upon seeing epsilon, you will be in Q0. Apart from that, if you look at this DFA diagram, Q0 upon getting 0 comes back to Q0 itself. Okay, that's one possibility. Again, there's one more possibility from Q1. From Q1, if you're getting a 0, you can reach to Q0. So these are the other two possibilities other than epsilon. So it can be written as epsilon plus Q0 with 0 plus Q1 with 0. So this is the expression for Q0. Now let's write the expression for Q1. So if you look at Q1, if you look at the state Q1 is also a final state here. Okay, Q1 is also a final state. There's only one way to reach Q1. That's from Q0. If you see a 1, you are at Q1. That's the only way to reach Q1. So we have to write it like Q0 with 1. Okay. Now when you look at these two expressions, and we want to formulate it in terms of the something like the Arden's format. Okay, so what we can do here is that we can notice that here is a Q1 here, and Q1 is also here. Okay, so we know what's Q1, and we can actually if you substitute this Q1, this Q0 into 1 here in this Q1, we can actually take Q0 outside and make it in the format of the Arden's format. Okay, so let's try that. Okay, so what essentially I'm going to do here is that I'm going to apply 2 in 1, applying 2 in 1. Okay, now that becomes that. So if you apply that, it's going to be epsilon plus Q0 dot 0, and instead of q1 I'm going to write this one, that is q0 dot 1, q0 dot 1 dot 0. Okay, now it's very clear that you can take q0 outside, so it becomes epsilon plus q0 inside the bracket. You can write 0 plus 1 0. Okay, so if you combine this, then it is actually q0 dot 1 dot 0. That's why we are able to write it like this. Okay, so epsilon plus q0 into 0 plus 1 0. Now if you look at this expression, this is similar to the Arden's format. Okay, so you can consider this as R. This is also R. Now this string can be considered for P, and this is going to be your Q. Okay, so this is in the Arden's format. So we can write Q0 as, from this we can say that applying the Arden's rule, we can identify that Q0 is going to be QP star, that is nothing but epsilon into P star, that is 0 plus 1 0 star. Okay. Now epsilon dot anything is epsilon dot 0 plus 1 0 star is nothing but 0 plus 1 0 star itself. 0 plus 1 0 star. So we got a very nice expression for Q0. So we got a very good expression for Q0. Now remember that in the DFA that we obtained here, both Q0 and Q1 are final states. So the equivalent expression for this DFA is going to be the expression for Q0 plus the expression for Q1. So now that we got Q0, we can write the expression for Q1 very easily. So Q1 can be, so from here, if you look at this, okay, so since we have got Q0 as 0 plus 1 0 star, we can substitute it here. So Q1 is going to be 0 plus 1 0 star into 1. Okay, so now we have to combine both of this. So what we want is the regular expression for Q0 plus the regular expression for Q. So the final answer, I'm going to use a different color to represent the final answer. So the final answer will be a union or the plus operation of this particular regular expression and this particular regular expression. Okay. So that means the final answer is going to be, let's write the expression for Q0 first. That is 0 plus 1 0 star plus the expression for Q1, that is plus the expression for Q1 is 0 plus 1 0 star 0 plus 1 0 star into 1. Now this entire expression is going to be our answer. That is 0 plus 1 0 star plus 0 plus 1 0 star dot 1. Now, as an assignment, you can try the following. So you are given with two FAs. You can convert it into its equivalent regular expressions.